All right, welcome to another exciting episode of AP Chemistry here at Spain Park High School. It is Monday, October the 16th, 2023. And if you are enjoying these videos, please feel free to hit that like button and ring that bell. Subscribe to my channel too. I think I might be up over like 105 now or 106. Gotta start bringing in that money pretty soon. Yeah, that's my retirement plan. I'll be working for a while. Okay, on Friday we were talking about Bohr's model of the atom and how he figured out that how is hydrogen, when you're looking at this hydrogen, through the spectrum glasses, you're seeing the red, the teal, and the purple line. How is hydrogen giving these bright line spectrums? What is it about it? How can this be happening? Because classical physics said that the electron, a charged particle rotating around, ought to be giving off and emanating energy and just cave into the nucleus, but it didn't. So Bohr just said, well, it doesn't cave in, so it must have a fixed energy. Okay? Must have a fixed energy. And he was able then to calculate the fixed energy. Now I added in another little variable here. Z, which is the atomic number. Now what's the atomic number of hydrogen? One. So it doesn't really play in to the hydrogen atom at all. But when you go and apply this to other atoms and put the Z in there, because you start getting electron-electron repulsions and the electron cloud and there's different things, it just didn't work. Now we're still going to use this base model. We're just going to modify it a little bit. And then, so Bohr has this here, and he's able to explain it, the hydrogen atom, but it didn't go any farther. So scientists, there's so much happening in the 1920s that Erwin Schrödinger was taking this, and there was that movie that we were talking about, The Clash of the Titans, okay? Big debate. In the 1927, they had a big conference, and they were arguing, and the Clash of the Titans was Niels Bohr with Werner Heisenberg were clashing with Erwin Schrödinger and Albert Einstein. And they back and forth for a whole week. They would give their proposals, and then they would argue, debate with one another. Then they would go home that night, and they would just kind of try to refigure everything out. And I wish I could had time to show the rest of the video. You can see it online if you want to go and watch it on your own. But it talked about Niels Bohr would just be so distraught, that he would go home and sometimes he would cry, just because I know I'm right, but us Einstein's, they're just knocking everything down. But turns out, though, by the end of the week, Bohr and Heisenberg were the ones that were more accepted. But what Schrödinger was proposing is that, well, Einstein said that light has a dual nature, and a guy named de Broglie came along, and he found out this thing called matter waves. And he found out that the wavelength, I can never remember the stupid equation. But he found that you could calculate the wavelength of any particle in motion. So when I'm hitting my 100-mile-an-hour tennis serve down the tee, that ball's going, it looks like it's going pretty much in a straight line, but the reality it has a wave, actual wavelength. It's got a wave nature. Now, for macromolecules, the wave properties are insignificant. Somebody look up in the book, look in the index, and look up de Broglie matter waves. Look up matter waves in there. It's the wavelength is equal to hc over something. I can't remember what it is.
Hey Siri. Matter wave. Oh. Hey Siri.
I wish we had a pause button here.
Well, they can deal with it. Matter.
The term used to describe the wave characteristics of a moving particle.
Right. I know. I just want the equation. Wavelength.
What is the wave? Electron moving. That's not the question.
Okay, but do they turn to go to the previous page? Does it not give?
I'm fine.
There it is. Yeah, right there. H over mv. Okay. So matter waves. This was Louis de Broglie. Matter waves, which is the wavelength is equal to, what was it, mv over
H over MV.
h over mv. Okay? H is Planck's constant, m is the mass, v is the velocity, because it's a moving particle. It's a pretty easy math equation. Any moving particle has a wave characteristic to it. Now, this is equal to 6.626 times 10 to the minus 34 joules. If you put in a mass of a tennis ball and the velocity of a tennis ball and divide it in, it's still going to be a very, very, very small number. The wavelength is going to be so small it's undetectable. It's irrelevant. But when you get down to the size of an electron and an atom, and you put the mass of an electron traveling near the speed of light, the speed that the electron's traveling, then the wavelength gets very measurable. And it turns out that it's about the wavelength of an atom. So that was de Broglie. So Schrödinger, Erwin Schrödinger, okay, he developed the wave theory of electrons. So he was able to describe everything that Bohr described, but in terms of an electron being a wave instead of it being a particle. Now he considered it to be a standing wave. Okay? So Wesley, come grab the other end of this. Go stand against that wall over there. Okay? Yeah, your job is stand against the wall. Go ahead, keep going back. Your job is to not let go. All right? All right. So if I send a wave down, you can see it that it bounces back and forth. Okay? It's bouncing back and forth. Okay? But there's constructive and destructive interference with a wave. That crest meets crest and trough meets trough. They get double high when a crest meets a trough. On the way back, they cancel each other out. So if I can get things in the right rhythm, now we have what's called a standing wave. It's called a standing wave. Try to hold your hand as still as possible. Okay? It's a standing wave. And it doesn't appear like the energy is moving. It looks like the crest is just going up and down. But the reality is that the wave is going back, bouncing off, crest is meeting crest, trough is meeting trough. Okay, Raul, come here. Okay? I know you're not in band, but let's see, hopefully you have this much rhythm where you can make this keep going. Okay? For real. For real. Go big. Go home. Okay? You can kind of see that right here is a node. That's where crest is meeting trough and they're canceling each other out. It's a standing wave. Okay? Now, okay, so now you can really see that node right there. That's where a crest is meeting trough. There's destructive interference. So now, if I change the wavelength, now I have 3 waves and I have 2 nodal areas. But notice that the number of crests is still a whole number. Between Wesley and I, there's got to be a whole number. Now if I change the wavelength again, get my arm loose. All right, here we go.
You got 3 nodes.
Okay, now we have 3 nodes. Okay, but notice the crest is still a whole number of crests. Got me? Mm-hmm. So each, okay, great job, Wesley. All right, you did not let go. So Schrödinger said the electron is in this standing wave type. That's called a standing wave. It appears like the wave is not going anywhere, but the reality is it's rebounding back. It's in the standing wave pattern. Now, when Schrödinger explained everything, he went into a 3D standing wave pattern. But he used the same concept, that there's only certain distances, certain wavelengths that this standing wave pattern can form. When Raoul was trying to do it, he didn't have the right rhythm, and we had more chaos than we had a standing wave pattern. There's only certain wavelengths that it can happen. There's only certain distances from the nucleus that this standing wave pattern, based upon the energy the electron has, only certain distances from the nucleus the electron can be. He was able to explain the whole idea of this, and he came up with this exact same equation, just from a wave perspective rather than a particle perspective. So then Werner Heisenberg came along, and y'all watch Breaking Bad?
Yes, Heisenberg.
Okay, so he was Heisenberg. That's what the name. He needed a street name, so he just thought of something to name from science, from his chemistry class. Okay, and he did the uncertainty principle. The uncertainty principle that simply says that location and energy cannot both cannot be known, I should say, cannot both be known exactly. The more you know of one, the less you know of the other. In order to find the location, you've got to change its energy. In order to find its energy, its speed, you got to change its location. More of one you know, the less of the other one that you're going to know. Okay? Bohr was still thinking that the electron was kind of like in an orbit. Schrödinger said, no, it's in the standing wave pattern. Well, where's it going to be? Schrödinger and Einstein wanted it to be a little bit more definitive. Heisenberg described everything in terms of matrices, a very complex math matrices, which is way over my head. But Einstein said there's no way we can just describe matter, this concrete matter, in terms of mathematical matrices and probabilities. Yet, that's where we are today. And so instead of saying that the electron's in an orbit around the nucleus, we say that it's in an orbital around the nucleus. And an orbital, does anyone remember the definition? Anybody remember the definition? Is the most probable place to find an electron. Okay? Most probable place to find an electron. All right. Just hit stop.